So, last class we derived the mean momentum equation. Okay. So, now this was the equation written in the notes here. This is taken from the last class. So, this is the mean momentum equation. Now, let me first talk about what we call as the closure problem of turbulence. I started with which equation? The Navier-Stokes equation for instantaneous velocity. I divided them into the instantaneous velocity as mean velocity and a fluctuating part, and pressure also as mean and fluctuating part. Then I take the mean of the Navier-Stokes equation and I get these equations. Okay. So, now this gives me, if I look at this, this gives me an equation for so I have an equation for mean of ui, and I can consider this as a mean of equation for mean of pressure. So, totally now when I count, I have 3 equations as the first one and 1 scalar equation, 4 equations, 4 unknowns. But then what I find is that in these equations there is this term and there is no equation for this term. And this is what we said, that now, so the set of equations so the above set of equations is unclosed or not closed. So, what do we mean by closed set of equations? Where the number of variables is equal to the number of equations. So, that is the meaning of closed. So, closed set means number of dependent variables is equal to the number of equations. And clearly this equation set is not closed. And if this equation set is not closed, that means we have basic, so we need an extra equation for ui prime uj prime. So, the first question which comes to our mind is, we started with a closed set of equations, we did some mathematical manipulation, and now we end up with a set of unclosed equations. Can that mathematically happen or not? And the answer to that is, what is the procedure we have done to those equations? We have taken an average. So, when we take an average, clearly in the average we lose out details. For example, if I say I have 5 numbers and I say I represent these 5 numbers by their average, obviously the average does not convey as many details as the total original set. So, when we do the averaging, we have lost out some information, and one of the manifestations of that is that we end up with also an unclosed term. Okay? So, that is why this closure problem, and this what we say. So, we need extra equation for mean of ui, uj, take the total mean of that. So, that we need an extra equation. Now, one can say that let us let us write the equation for ui prime uj prime. We will do that, but a bit later in the course. But how do we do that? For that, what you will have to do is, first we write equation for ui prime alone, just the fluctuation without the average. Yeah. No, so assumptions like homogeneity, etc., will be used to write what the ui prime uj prime is. And this is what we will call as modeling. That if we express ui prime uj prime in terms of the other variables for which we are solving, or something else which is known in the problem, that is what we will term as modeling, and some sort of closure approximation. But if I need the exact equation, then I need to get an equation for ui prime uj prime, average of that. And how do we get that? First we will write the equation only for ui prime. And this, as I said in the last class, we write this equation by taking equation for ui and subtracting the equation for mean of ui. So, this we will do this. It is a tedious exercise, but we will do it, but not today, maybe 1 week or 2 weeks later, or maybe even more. So, we will come back to this, but that means we can write the equation for ui prime. Now, if I have written the equation for ui prime, do I need a separate equation for uj prime, or is it the same equation? It's the same equation, you have to just change the index I by j. So, and then what you do is, how do you get the equation? The equation for ui prime, if I multiply by uj prime, and the equation for uj prime, if I multiply by ui prime, I will get an equation for ui prime uj prime just by itself, no averaging so far. So, we will write this and then take equation for ui prime, and we take the equation for, and we multiply by each term by uj prime, and take the equation for uj prime, multiply each term by ui prime, and add these. This will give equation for ui prime uj prime. Now, right now it is without average. And how we do that, let us not bother about it now. We will come to it, maybe I will float it as an assignment telling you how to do it, and then you can try it out at home and do this. Now, what you will find is this equation for ui prime uj prime, right now it is not averaged, this contains ui prime uj prime uk prime. This equation will contain now a third order term, okay, and it will also contain terms like ui prime p prime. So, the equation for ui prime contains these terms, and when you average it now, then you get equation for ui prime uj prime, and this contains average of ui prime uj prime uk prime, average of ui prime p prime, etc. And this is sort of fairly straightforward to see that how these terms will going to come in, because you have an equation for ui. If you even look at just the Navier-Stokes equation and multiply it by uj, then the nonlinear term gets multiplied by a uj. So therefore, a third order term comes in, and in primes it comes like this, and there will be more terms. So what this tells you is that even if you write the equation for ui prime uj prime, you don't close the set of equations. Why? Because you will get more unclosed term or higher order unclosed terms. The equation for ui prime uj prime contains ui prime uj prime uk prime average. Now there is no equation for ui prime uj prime uk prime, and there is no equation for ui prime p prime. Our equations are only for mean of ui, mean of p, and also for mean of ui uj, if we write this. But there is no equation for ui uj uk average, third order term, or an equation for pressure and velocity correlation of these. And this keeps on happening. You write the, so then you say, okay, let me write the equation for ui prime uj prime uk prime. It will contain a fourth order term, and so on. So therefore, this averaging procedure will never, so second order equation, which means equation for ui prime uj prime, contains third order and other unknowns, and by writing equations of higher orders, we keep on getting more unknowns. And this is what we call as the closure problem of turbulence. That you may keep on obtaining orders for higher order quantities, but you will never be able to close the set of equations. So what does one do? In absence of this, what one resorts to is so we have to resort to what we call as turbulence modeling. And so, for example, the unclosed term ui prime uj prime has to be expressed as a function of the other closed dependent variables. And in this case, we have the dependent variable is mean of u, mean of p, or properties like nu, etc. So if I write ui prime uj prime as some function of the mean velocity and put it back in the equation, then the equation becomes closed. And so this is what we call as the closure approximation, and this is what one does in turbulence modeling. So we have this, and this is called the closure approximation, expressing unclosed term as a function of closed terms. And this whole process is what we call as turbulence modeling. Now, from what I have described here, you can see that the turbulence modeling could happen at many stages. The first stage is I say, okay, I am only going to solve for the mean velocity. So, in the mean velocity, I have ui prime, uj prime. I write this as a function of mean velocity. So, this is the first level of turbulence modeling. At a second level, I may say, no, I think I am not getting such good equations. Let me write the equations for ui prime, uj prime. So, I will write the equation for ui prime, uj prime, but the third order terms and the terms like pressure times ui correlation, I express them as closure approximations. But now when I do that, I can express ui, uj, uk not just as function of mean velocity, but I can also express it as a function of Reynolds stress, because I now have an equation for Reynolds stress which I am solving. So, that would be closure approximation at a second level, and there are different names. The second level approximation is called second order modeling or Reynolds stress modeling. So, one could close at somebody says, no, I am not happy with second, let me go to the third step, third equation for third order, I close it at that level, and so on. So, this is what could happen, and this is what is basically what the problem of turbulence is all about. And of course, the other way could be you say, no, I will just solve for the instantaneous velocity. I do not need to do any of, if instantaneous equations are closed, I do not need to, I can solve them. But then what is the issue there? Why do not I solve for the instantaneous velocities? Very high computational expense, because the scales are very small. As we have seen, that you will have to resolve at least to the Kolmogorov scales. And for a typical turbulent flow, these scales are if you look at the number of grid points which comes, will be very large. It goes like Reynolds number to the power of -3/4. So, in 3 dimensions, it becomes Reynolds to the power of -9/4. So, even for a steady flow or statistically steady flow, if you are solving, you need so many grid points, and which by any stretch of imagination, any computational this thing is not going to be possible. And so, that is why you need modeling. Okay. So, this is basically, so now, so what we do is in many closure models, we relate tau ij, which is equal to minus rho times ui prime uj prime to the mean velocity gradients. That is the most simple form of the models which we can have, and here also we will see there is a wide range of models or things which come in here. Okay. Now, similar to this, if I look at the equation for transport of heat, so this is what happened in the turbulence case. In heat again, if I look at it, the equations are partial theta by partial t plus uj if this is the equation, and we write uj is equal to mean of uj plus uj prime, and we write theta as mean of theta plus theta prime. Then when we put this in, what we get is partial mean of theta by partial t plus mean of uj d theta by dxj plus partial by partial xj of uj prime theta prime. This is equal to gamma times d2 theta by dxj dxj. So, this is the equation for temperature or the heat transport equation, and for stationary flows, one can write it as mean of uj d theta by dxj is equal to d by dxj of gamma times d theta by dxj minus uj prime theta prime. And this term, so basically this is just like the velocity equation, but now what we have is instead of ui uj, I have a theta prime uj. And this term uj prime theta prime is sometimes called the turbulent heat flux. Yeah. Oh, I'm just writing the equation that if there is a flow where there is heat transfer also. So then just analogous to the Reynolds stress in the turbulent flows of that type, I will get a turbulent heat flux. So this I've just got for, because you may encounter this also. Particularly if we have a flow with buoyancy, then in fact your Navier-Stokes equation will also change, but then that has to be solved in conjunction with the heat transfer equation. So this is just right, I think, why, because I'm going back to the Reynolds stresses and we'll focus more on Reynolds stresses. So, yeah, last equation, okay. So we'll even I was doubting whether or debating in my mind whether I should bring it here or should I bring it later when it is needed, but I thought at least let the equation be there for the sake of completeness.
So this uj prime theta prime
Is the turbulent heat flux.
why are you calling it stationary flow?
Oh, stationary means I have taken partial theta by partial t to be 0, the mean average.
So that would make it steady flow rather than.
No, no, if it is for average, that is what we said stationary. Steady will mean the instantaneous is 0. In steady flow, the instantaneous quantities do not change with time. Here the variable is changing with time, but on an average sense it is not changing with time. So stationary is the difference between instantaneous and average. Okay. Now let's spend a bit of time on this Reynolds stress tensor. Reynolds stress term, and actually it is a second order tensor. So let's, and this tensor I write it as ui prime uj prime average. So there may be a rho or without a rho. If you have to equate it with the stress, then a rho has to be multiplied, but if this rho is a constant, then basically in a lot of literature we refer to just as ui prime uj prime as the Reynolds stress tensor, and that rho doesn't make so much of a difference. So now first thing is, if we look at this, so this will look like u1 prime square, u1 u2, u1 prime u3 prime, u2 prime u1 prime, or this is the components. No, I wrote it like a determinant, but these are the components of ui prime, uj prime. And let's say this is equal to tau ij. Now let's try to identify the properties of tau ij. What are the properties of tau ij tensor? Anything comes to our mind? What all can you think? Think of anything which is related to this tensor. One is it is symmetric. Does everybody see that? Because the cross diagonal terms u1 prime, u2 prime average has to be the same as u2 prime, u1 prime. So it's very clear that firstly this is symmetric. It means tau ij is equal to tau ji. And this makes it that there will be so the number of independent components of this will be 6 and not 9. In general, a 3 by 3 matrix has 9 components, but because of symmetry, the number reduces to 6. Okay. Then a second thing which then other thing which we do is we define K as the turbulent kinetic energy is equal to such that K is equal to half of ui. Okay. So for the first time in this course, we have introduced the concept of turbulent kinetic energy. Now ui means there is a summation convention. So this will be equal to half of u1 prime square okay, just sort of, and it seems to make sense because how do we define kinetic energy? Ui prime prime. In fact, that's what I said. If it is small letter, then sometimes I may, but it's good you pointed out. I have to put a prime. Okay. So this is a turbulent kinetic energy, and we will see when you talk of, some of you have used the K epsilon model. The K term which you talk of is this, and in some sense physically, well, of course its dimensions are what, meter square per second square. That is another thing we should always keep in mind. When we look at things, any new quantity which comes, we should immediately try to think of what is it dimensionally. Because as we have seen, dimensional arguments can lead us to a lot of important conclusions. So this is the turbulent kinetic energy, and as I said, if you use the K epsilon model, then the K term actually is the same K. Epsilon is a dissipation whose mathematical definition I did give, but it has not come in. It will come in once we derive the equation for K. Then we will get a dissipation term in the K equation, which will be the mathematical definition of K. But we have seen the estimates of epsilon, and we have already seen the order of magnitude of epsilon, etc. So therefore, what we have is So next what we do is, let's have a look at this, that any tensor, second order tensor Aij, it can be written as equal to, I can write this tensor which is equal to, let's say, A11. Now this is symmetric or not symmetric, it doesn't make a difference. A21, A22, A23, any tensor, again I should put a bracket, not a this thing. This can be written as, and what I do is, I write it as A11 plus A22 plus A33 divided by 3, A12, oh sorry, 0, 0, 0. Now I will use the notation AII, 0, 0, AI by 3 plus, and again it's no rocket this thing, it will be equal to A11 minus AII by 3, A12, A13, A21, A22 minus AII by 3, A23, A31, A32, so I can divide this into two parts. You may of course ask the logic rationale for doing that. Why are we doing this? What is the reason for doing this? Now, when I look at the first part, what do you find about this? That all the diagonal terms are the same and all the non-diagonal terms are 0. And how can I represent it in tensor notation? I can write this as AKK upon 3 times delta ij. Delta ij is the canonical delta, which is equal to 1 if I is equal to j, it is equal to 0 otherwise. So therefore, this can be written as, this whole tensor, the first part can be written as AKK by 3 times delta ij. Is that clear? Just see this, because when, so this will mean this is equal to whatever A prime ij, where A prime is this part. I have divided A, and this first part I can write it as AKK by 3. Notice I did not use I or j here. I used some other index because I wanted to use delta ij. So this very aptly represents this. Now what happens is, a second order tensor which is proportional to delta ij multiplied by some constant, is actually what we call as an isotropic tensor, which means if I rotate, it's in any rotated coordinates also it will show up as the same value. So delta ij, if you, so that means I have delta ij, if I rotate my coordinates, again I will get the same value, components will be 1, 1, 1, 0, 0, 0. Yeah.
Sir, I have a doubt. Like, you have written AKK del ij.
Yeah.
Even if we do ij,
Yeah.
del 1 2 will be 0.
Yeah, so del 1 2 is 0, so this component is 0.
Yeah, so even if we use ij, then it will be same. Like,
No, ij means what?
2 and 3, 3. For example,
No, if I put I is equal to j, if I take I'm not, see now what will be, let's say this component, this vector is equal to, this tensor is called Iij. I give it a name, it's a second order tensor, so there have to be 2 free indices. I call it Iij. Suppose I call it this way. Now what is I11?
that is
It will be AKK by 3 times delta 11. So it will be AKK by 3. What is I12?
0.
I13, 0. So that's why I am writing it like this. So now what is your doubt?
Sir, the entire rule like from I1 to 3. So A11 del I j, that is I is equals to j, then A11 del 11. So that is
No.
A11 by 3
See,
plus
Kk means it's a summation. Kk means it's not A11. Kk means you are summing, so it's A11 plus A22 plus A33. Once an index is repeated, it loses its meaning. It has to be summed upon. So that is why I used AKK here. So AKK means A11 plus A22 plus A33. Because in each of these Ij, this K cannot show up alone. K shows up as a sum, so you always have to sum. Okay. So this is what this index looks like, and this part Iij, this is what we call as the isotropic part of Aij. Okay. So now the second part which you have, this is the remaining part. Okay. This remaining part we call it as, again there is a mathematical name given to this, deviatoric part of Aij. So any tensor Aij can be split into two parts, Iij plus Dij, where I is the isotropic part, D is the deviatoric part. How many independent components were there in Aij? 6 or 9? 6 is if it is symmetric. If it is general, then there will be 9. Now, when I split it into two parts, how many independent components should totally I get? Again 9 only. Now, so there, but now here we have 9 components here and AKK by 3. That makes it 10. ठीक है ना? So then how come we have got one extra component? See, if you look at it, the first one has AII by 3. So there is one component there. And there are 9 components here in the second part. So totally I have got 10 components. Which are the 9 independent components? So how do, that's the question I am asking.
Because AII is dependent on the other 9 components, right? So it's like pre-calculated in a way.
Yeah, it is like pre-calculated, but then, so, but there's, AI is there, but then if I split into these two parts, I get AI by 3, that is just one constant, and there are 9 constants here. So that means there has to be something in these 9 constants which is related. So what is the diagonal element or trace of this matrix? What is the trace of the Dij part, of the second part? What is the trace? Sum of the diagonal elements. That is 0. So therefore that gives you the extra relation. That when you break it up, so you still have 9 independent components. So now any tensor, second order tensor, you can break into two parts, an isotropic part and a deviatoric part. And the deviatoric part always has a 0 trace. Because even when you rotate, the trace does not change. That is an elementary property. So we can write Aij, any tensor can be written as Iij plus Dij. So this is the isotropic part and this is the deviatoric part. And by definition of deviatoric part, dkk will always be 0. Okay. So, Iij is always equal to akk upon 3 delta ij, and dij is equal to aij minus iij, and dkk is equal to 0. And the same thing now, once I have, this is the general A tensor, and why I was doing the general tensor, I can use this splitting for Reynolds stress or tau I. So then I can write using the splitting ui prime uj prime. This will be equal to plus the remaining part, or the deviatoric part, I write as aij, and this aij is written as the anisotropic part of Reynolds stress tensor. There was an isotropic part which is 2/3 k delta ij, and the remaining part which we call will be the anisotropic part. Now what you will realize is, how does this equation appear in the mean energy equation? D by dxj of ui prime uj prime. So when I take a d by dxj of this whole term in this way, if I take d by dxj of 2/3 k delta ij, then that becomes 2/3 times partial k by partial xi, because if the d by dxj and delta ij, there is a rule, or the summation goes, when you have a common index with delta, then whatever comes in front of that, the common index goes away and we replace it by the second index. This is the summation convention, how it works. Okay. And again, if there are issues, all of you have the 711 note, there is a Cartesian tensors by Pope. That chapter has been already put up on Moodle. So you can please go to that, and in fact some of this is also given there, maybe with different notation. So what will happen is that this term, 2/3k term, can be combined with the pressure term, because the pressure term also comes as d by dxj as a gradient. So this term combines with the pressure term, and we are left with only the anisotropic part of the Reynolds stress, which basically, in fact, when we say, normally we talk of u1 u2 as the Reynolds stress, u prime v prime. We don't talk of u1 prime square, u2 prime square, u3 prime square, and the reason for that being that these terms which are there, the diagonal parts, they normally come out as a gradient and are clubbed with the pressure term. So the only thing which stays from there will be this term k, and we will work on this term k. So this becomes the main part of this Reynolds stress, which needs to be studied and modeled, and etc. Okay. So again, now what I am going to do is, as far as our course goes, in fact, so at this point I have talked a bit about Reynolds stresses, I have talked about the equation. I will now revert back to Lumley's book. We will first complete, we have done some of it, but we will complete chapter 2 first. Okay, in fact, I was hoping that I will start all these in chapter 2. The main thing which comes is that we look at the pure shear flow first, and we look at a laminar type of model first, and we look at what happens, how shear stress comes because of collision between molecules. And we derive an expression for the shear stress in terms of molecular properties, which would be essentially the laminar way. And then we will look at the how it happens in turbulent flows physically. So that we will look, and then we look at the boundary layer. So now as far as the course goes, what I am going to do is I will first cover, I think up till chapter 4 or maybe 5 of Lumley's book. And then I will go on to the modeling part. And towards the second half, I will then talk of what the different turbulence models are and how do we write them and how to use them.
So can we say that what we have done with Reynolds stresses, we have also broken this into isotropic and
Yeah, that's what we have done actually. Yeah, that's right. We have broken. And then the deviatoric part we are saying is anisotropic. How do I get term anisotropic means not isotropic. So that's why that means the other part is isotropic. Definitely we have done that. So we have broken the Reynolds stress part into tensor into an isotropic part and a deviatoric part. Okay. So but चलो देखते हैं, maybe tomorrow now is a Tuesday, tomorrow is a Thursday schedule. Tomorrow is a Thursday schedule. Should we meet tomorrow?
Yes, sir.
I think let's meet tomorrow also. Is that fine? थर्सडे को तुम्हारा लेक्चर होता है 11 से 12, अब 12 से 1, कौन सा स्लॉट है? एच, अच्छा जो भी है, तो तुम्हारा थर्सडे और मंडे, थर्सडे और वेडनेसडे को भी होता है. सो कैन वी मीट वेडनेसडे?
सर वेडनेसडे को तो आपकी रेगुलर क्लास
नहीं, वेडनेसडे को नहीं होती.
सर वेडनेसडे को तो वीकेंड
कल 11 से 12 में एफ स्लॉट पड़ेगा. देखो एफ स्लॉट में सब बच्चों की क्लासेस होती हैं काफ़ी, तो 11 से 12 विल नॉट बी पॉसिबल. सो वेडनेसडे को आई थिंक इट शुड बी पॉसिबल. वेडनेसडे 12 to 1 इज ओके. तो ठीक है, देन इवन दो वी हैव, बट विल मीट ऑन वेडनेसडे 12 to 1, बिकॉज मेरा फर्स्ट लेक्चर भी वी जस्ट गॉट मिस्ड एंड ऑल्सो let me get to something. So Wednesday we'll meet 12 to 1. And then again I think Thursday is a holiday and this Friday is a no class day. So let's meet on Wednesday anyway. तो अब Wednesday को भी आ जाएगा, ठीक है ना, 12.